So looking at the decimal number 96, we are looking for a 1 on the 64, we're looking for a 1 on the 32. So that's our 2 bits that we're looking for. So if we go down and have a quick look at those, what we need to do is in our logic is just do an and that will turn our light on or be our result. So in the case of the video logic we're looking at now, this would be maybe the front porch or the back porch, horizontal sync or the vertical sync for what Benita was trying to do. And what we're trying to do is just determine what type of logic we need, and the simplest way of doing it, just to say, okay, I've reached the number 96. When I've hit 96, I want to reset my counter and we'll carry on. So in this case, 96, very easy. We can just use a standard AND gate and boom, we've got the number 96. We've used 64 and 32 bits. Once they've lit, we've gone, we've flagged something, we've done something, and we can hit the reset button on our counter. Counter goes back to 0, never hits the 128 bit, doesn't need to, and we carry on from there. So moving on from that one, actually I'm just going to move back a step so we'll see which other one we're looking at. So we've got the number 100. Again, this was what I first said in the video, in the last video, in video 1, was we want to look at how we do this number. So this number is a 3-bit. We do actually have a 3-bit AND gate. It's available to us. So we could just use 3 bits and do an and the light will become lit, or various other things. We can make an action when we hit those 3 bits and they're on. What we also want to do is look at the ways of using other chips to basically turn on when we've hit either 3 bits or 4 bits or 5 bits or 6 bits or 7 bits, and we need basically an 8-bit AND gate, which is where we can either say our 8-bit AND gate is our standard and we need to invert all the other bits, so all the zeros we want to turn to 1s, because we just need to turn on our AND gate when we know our 1s are on, and the other zeros we'll just turn them on for the heck of it, which is an easy way, but we need more chips to do that. So I think being economical, we need to look at how we can make these things affordable to ourselves. We don't need these chips if we are just doing an AND gate for 2 or 3 items, but when we come down to the 8 items, where we need to know an AND for 8 bits, which will be the last one, so the 103 decimal, that needs 5 bits, so we do need an 8-bit AND. However, with the 3-bit AND, we can get away with just a 3-bit AND. And so what I've done is, in the simulation, I've got both running. I've got the 3-bit running with an AND gate, but I've also got it running with an 8-bit AND gate through knotting the outputs where they're 0. So they come out as 1 because we know they're already 0. We're not interested in that. We just want to know when our 1s become 1, which is our 64, our 32, and our 4. Just a quick recap on this one. So we're going to be looking at the numbers, decimal numbers, 96, 100 and 103. Okay, those are 2 bits, 3 bits and 5-bit numbers in binary. So what we need to do is to basically go through these, and on the 96 decimal we can have a 2-bit AND gate, turns our light on, resets our whatever we're doing, our front porch, back porch. And if we're looking at the 100 number decimal, we need 3 bits, so we can use a 3-bit AND gate. That exists, that's fine. Okay, so if our desired number is 100, we can turn on LED or reset the flag. We can reset the binary counter and we go back to the beginning. When we hit the 103 that we're trying to look at, it's 5 bits required, but there is no 5-bit AND gate, so we have to use the 8-bit AND gate. So we can either use all across the board the 8-bit AND gate, or a mixture and a match of various ones. In this case, what do? So basically what we need to do is look at the numbers. When we want to know the number is 103, the yellow items we want to be on. That is our 103 value. But we've got an 8-bit AND gate, and the 8-bit AND gate will want all of the bits to be on. So what we need to do is to take the bits that are currently not on at that moment in time, so the 128-bit, we've got the 16-bit and the 8-bit, and we need to turn them on. The way we turn those on is we use a NOT gate. So we say NOT those, they become 1, and then we pass them to our 8-bit AND gate where they become one value of on. So the very fact that we've got our value of 103 can only be true when all of these ones are on. And the fact that we've sort of like virtualized the other zeros to be on is purely to get our gate to work and turn on. The values in yellow are the ones we're interested in, and they are what actually will make the gate work. So the red ones, the zeros we've fictitiously basically made one, are quite irrelevant. They are only there to use in the gate to make the whole thing work. But this is a great way of logic with the 7400 series logic anyway, is to say I need to find out a weird number like 103. I need to know when these 5 bits are on, but the computer, which is what we're building, basically says, well, I need to know what all 8 bits are. And you say, well, okay, I know which these 5 bits I need, I'll just turn the other 3 bits on. Right, so we're back in Atanua, and I've made a few updates to the last diagram that we were working on. And what we have now is we've got the same 8-bit LEDs, and what we've also got is a backwards and forwards button. So this is our count up, count down. This blue LED represents the number that we're trying to get to, which is 100. This white LED represents the number we're trying to get to, which is 100. But we're trying to get to them in 2 different ways. So what we've got is, if we look back to what we were just talking about, we have the need for 3 bits to be on for the number 100. So I've taken all 3 bits and I've passed them into this AND gate. And in the AND gate we need all 3 bits to be on, and this will make our light light. And this is basically our action. So if our action happens, we're happy. What I've also done is taken all 8 bits and I've passed them to another chip, which is the 7400 series 04. It says Hex Inverter. What it actually does is it takes each input and it will NOT it. So this input, which they call A6, will have an output called Y6, and Y6 is what we're taking through, and what we have here is what is a standard logic gate, and this is our 8-bit AND gate. So all of these 8 bits have to be on in order to turn this lamp on. And in our scenario where we're just trying to look for the number 100, we can use a 3-bit AND gate. But if we were using a more complicated number, we would have to use this. So we'd have to introduce this 04 chip with the 8-bit AND gate. So in, I think, Benita's case, he's probably used this method for everything, where he just has a knotted version, so an inverted version of everything, and a regular version of everything. But what we'll do is we'll just prove the point. So at the moment we've got these bits on and these bits, and we're going to increment by 1, and we've now got a blue lamp on, a white lamp on. So we've hit our value, so we know we're at 100, and we've done it in 2 different ways, which is fine. The cheaper way is obviously we didn't need to use this 04 chip, and we didn't need to use an 8-bit AND, which is probably more expensive than a 3-bit AND. All we needed was a 3-bit AND. So I guess the moral of this is we can use a 2-bit AND, a 3-bit AND, but if we're going to get more complicated, we're going to need to bring in more chips and work out what numbers we're actually looking for. And these are very specific because we're not using software, this is purely logic. So we have to be logic based, know what exact number we're looking for, and then we'll continue on from here. So I hope you can use this one and maybe rebuild this circuit, use both versions and play around with it, and we will see what happens when we get on to video 3, which is where we're going to take it to next. Okay, I'll catch you on the next one. Cheers.